Welcome to the lesson 8.1 Conservation of Energy and Momentum. Here in this lesson we will discuss about the law of conservation of angular momentum for a system of particles. In the last class we have discussed the law of conservation of angular momentum for a single particle. Now the result can be generalized for a system of particles. For that, we consider a system of n particles. The total angular momentum of this system about any reference point will be the vector sum of the individual angular momenta of the particles about the same point. Remember, angular momenta are expressed with respect to some reference point. Say if J1, J2, J3 etc. are the angular momenta of various particles, then the total angular momentum of the system is J1 plus J2 plus J3 etc. This is the vector sum of individual angular momenta. So that is equal to J1 is R1 cross mv1, where R1 is the position vector of the first particle and v1 is the velocity of the first particle. Similarly, R2 cross mv2 etc. Thus, the angular momentum, total angular momentum J can be written as summation from 1 to capital N Rn cross mvn. Now mvn is the linear momentum of the nth particle, so that can be written as Rn cross pn, where n equal to 1, 2, 3 etc. up to capital N. That is the total number of particles. Here Rn is the position vector of nth particle, Mn, Vn, Pn are the mass, velocity and linear momentum of the nth particle. Now the net torque acting on the system will be equal to the rate of change of total angular momentum of the system, that is T is equal to dJ by dt. That will be equal to d by dt of summation n from 1 to n Rn cross Pn. So that is equal to, here it is a product of two vectors and we have to take the derivative. So we have to use the product rule, that is d Rn by dt cross Pn plus Rn cross dPn by dt. Out of that, dRn by dt will be equal to the velocity of that nth particle Vn, and Pn contains Mn Vn, and Vn cross Vn will be equal to 0. So that term will be equal to 0, only the second derivative term will be there, that is sigma n from 1 to n Rn cross dPn by dt. Now this dPn by dt is the rate of change of linear momentum of the nth particle. That is, by the second law of motion, it is the force acting on the second particle, that is F, on the nth particle, that is Fn. Therefore, the total torque acting on the system of particles equal to summation from 1 to capital N Rn cross Fn, where Rn cross Fn is the torque acting on the nth particle, that can be written as Tn. Thus, we see that the total torque is equal to the vector sum of individual torques acting on different particles. So, during this vector summation, this torque includes both internal and external torques. Internal means the force on the nth particle includes both internal and external forces. But during the summation, the internal torques cancel each other because the internal forces are existing in pairs of equal magnitude and opposite direction. This can be given from the Newton's third law of motion. Thus, after summation, all the internal torques will cancel each other and there remains only the external torque acting on the system. So this T will be the external torque acting on the system. So the net external torque acting on the system is T is equal to dJ by dt, where J is the total angular momentum of the system of particles. So this equation can be expressed in a sentence form as the rate of change of angular momentum of the system about any point is the sum of the torques about that point of all the external forces acting on the system. That is this P, that is the sum of the external torques. Or we can say that the external torque acting on a system of particles is equal to the rate of change of angular momentum of that system of particles. That is called the rate of change of net angular momentum of the system of particles. Now, if the external torque acting on the system is 0, then we see that if t equal to 0, then dj by dt is equal to 0, which implies angular momentum j is a constant. This is similar to the case of linear momentum. In the case of linear momentum, if the external force acting on a system is 0, then total linear momentum is a constant. Similarly here, the total angular momentum of a system of particles is constant if the resultant external torque acting on the system is 0. That is, in the absence of external torque, the total angular momentum of a system is conserved, and this principle is called the conservation of angular momentum of a system of particles. So the principle of conservation of angular momentum for a single particle can be easily generalized for a system of particles. Now we can express the angular momentum of a system in a more convenient form with the help of center of mass of the system. If capital R and capital V are the position and velocity of the center of mass with respect to the reference point, that is called the lab frame, and R and C and V and C are the position and velocity of the nth particle having a mass mn relative to the center of mass, then the position and velocity of the particle with respect to the reference point will be, by using the Galilean transformation, the position of the particle with respect to the reference point Rn is equal to position of the particle with respect to the center of mass, that is Rnc, plus position of the center of mass with respect to the reference point, that is capital R. Similarly, Vn is equal to capital V plus Vnc. Thus, the total angular momentum of the system with the n particles with respect to the reference point will be, R cross P, that is equal to Mn into Rn cross Vn, and this is the angular momentum of the nth particle, and if we take the summation from 1 to n, we get the total angular momentum of the system of particles with respect to the reference point in the lab frame. That is equal to n from 1 to n Mn into this Rn can be written as R plus Rnc, because Rn and Vn we have already written by using this formula. So using that formula, it is capital R plus Rnc cross capital V plus Vnc. That is equal to Mn sigma Mn. There are 4 times R cross V, then R cross Vnc, then Rnc cross V, then Rnc cross Vnc. Out of these 2 terms will be 0. That we can see that Rnc is equal to Rn minus R. Therefore, Mn into Rnc is equal to Mn Rn minus Mn R. Therefore, sigma Mn Rnc, that is this term, sigma Mn Rnc is equal to sigma Mn Rn minus sigma Mn R. Now, by the property of the center of mass, this sigma Mn Rn will be equal to Mr, where M is the total mass and R is the position vector of the center of mass. Therefore, this will be Mr, and this sigma Mn will be capital M, that is again becomes Mr minus Mr is equal to 0. Similarly, we can see that sigma Mn Vnc will be equal to Mv, which will be again, so by using this technique, this Mn Vnc will be also equal to 0, because Vnc is equal to Vn minus capital V. So by using the principle of center of mass, 2 terms are 0. There remains another two terms. The remaining two terms are this first term, that is sigma n from 1 to n mn into r cross v. Now this sigma n from 1 to n mn is capital M. Therefore this becomes m into r cross v, or r cross capital M into v. And capital M into v, we can see that this can be written as J is equal to r cross mv plus sigma, the last term, that is this term, Rnc cross Vnc. Now the summation in the second term, it is Rnc is the position vector of nth particle with respect to the center of mass, and Vnc is the velocity of the nth particle with respect to the center of mass. Therefore Rnc cross Mn Vnc is the angular momentum of the nth particle with respect to the center of mass. Therefore summation Rnc Mn Vnc is the total angular momentum of the system of particles with respect to the center of mass, and that angular momentum can be represented by Jcm, that is the angular momentum of the system of particles with respect to the center of mass. Therefore this can be written as Jcm, and this one, m is the total mass of the system, r is the position vector of center of mass, and v is the velocity of center of mass with respect to the reference point. Therefore mv is the linear momentum of the center of mass with respect to the reference point. Therefore r cross mv can be called as r cross p, where p is the total linear momentum, and this r cross p is the angular momentum of the center of mass about the reference point. Thus, the angular momentum of the system of particles about the reference point can be written as is equal to J is equal to angular momentum of the system of particles about the center of mass plus angular momentum of the center of mass about the reference point. So this is also similar to the Galilean transformation, in which the angular momentum of the system of particles in the lab frame is equal to angular momentum of the system of particles in the center of mass frame plus angular momentum of the center of mass with respect to the reference point. So this is the relation between the angular momentum in lab frame and center of mass frame for a system of particles. So after watching this video, you should be able to answer the following questions. What is the expression for the torque on a system of particles, and define the principle of conservation of angular momentum in the case of a system of particles. What is the relation between the angular momentum of a system with respect to a reference point and angular momentum of the system with respect to a center of mass frame of reference. Thank you for watching this video.